Hello and welcome to Business Analytics. In this introductory course, we are going to talk about analysis of variance. My name is Hari Rajagopalan and I will be your instructor for this lecture. So we are at Descriptive Analytics. We finished test of hypothesis, which we had two groups. We looked at one sample, two sample test of hypothesis. But what if we have three or more samples? That is more than three different groups which we need to compare. And if we do have that, we have to look at analysis of variance. Now, Excel has three ANOVA tests, and we call them single factor, two factor without replication, and two factor with replication. And we'll go through all three of them. Now, Excel does have a whole bunch of problems in its data analysis tool pack, and that's why this is just an introductory business analytics course. And if you do want to know more about analysis of variance or ANOVA, we would have to look at a much more extended package like Excel Stat, or there are other packages which do that. But right now, just pure Excel does not have that option. So let's look at analysis of variance. Now remember when you did your t-tests and you did those independent sample tests, you had to do an f-test to test whether the variances are equal or unequal. And ANOVA here, analysis of variance, uses this f statistic named after Sir Ronald Fisher. The variance, as you know, measures the dispersal of data points around the mean. So higher variance occurs when individual data points fall further away from the mean. And we all know that square root of variance is standard deviation, which is average distance from your mean. Now, variance is difficult to interpret because it's squared distance from the mean, and that doesn't make any sense intuitively. But it's easier to use in mathematical calculations. So F statistic is the ratio of the two variance or two mean squares. So variances, as we talked about, are the sum of squared deviations from the mean, where deviations is how far away from the mean you are. So let's take an example where the mean is 3, and if your value is 5, the distance from the mean is +2, squared deviation is 4, 2 squared, which is 4. So the larger the sample size, the bigger is the sum of squared deviations. Why? Because when you're adding up these values, the more your sample size, there's just going to be more values, and therefore you're going to have more squared deviation. So taking the average or mean squared deviation adjusts for this sample size, and that's why we take the mean squared deviation. Now, these f-tests are surprisingly flexible because you can include different variances in the ratio to test a wide variety of properties. So here, let's take an example, and we are looking at this analysis of variance. Here is a data which has 4 groups, and here are values you can have in these 4 groups. And really, we are looking to see whether these 4 groups are different from each other. So you can see here, the Excel will generate this thing for you. It'll give you the sample size, which is 10. It'll give you the sum of all this 10, which comes to 112.02. And for the second group is 89.37. But we really don't look at the sum. Here's what we're going to look at: average. Average for the first group is 11.2, second group is 8.9, third group is 10.6, fourth group is 8.8. So the overall average of all this data is about 9.91, as you can see. Excel also gives you the variance. Excel does not give you the standard deviation. So if you want the standard deviation, what you're going to have to do is take the square root of this variance and calculate the standard deviation as you see here. So you can see here that standard deviation is 1.9 here, 1.1, 1.87. So these two have similar standard deviations. This is slightly higher, this is slightly lower. And then you can look at, it'll give you an ANOVA where it's giving you sum of squares between groups. You have 4 groups, so sum of the squared differences between groups. And because you have 4 groups, your degrees of freedom is going to be number of groups minus 1, which gives you 3. And so your mean squared error is going to be 14.53, which is essentially 43.61 divided by 3. And your within groups is within these groups, your sum of squared comes out to be 158.46. And your degrees of freedom is each, here you have 10 minus 1, 10 minus 1, 10 minus 1, and 10 minus 1. That is 9 in each one of these groups. That is 9 times 4 is 36. And so your mean squared error is 4.4018. And using that, we can get our F value, and then we get our P value. P value corresponds, you can compare it to alpha. Your F value, you can compare it to F critical, which is your F value for your alpha. And if your F value is greater than your F critical, then, or your P value is less than your alpha, you reject your null hypothesis. Okay, so let's talk a little bit here. So your F value is basically your between group variance divided by your within group variance. Your between group, or the numerator, here we talked about average for each one of these groups is 11.2, 8.9, 10.6, and 8.8. The means of these groups is spread around, some of them above the global mean of 9.91, some of them below. The further the groups are from the global mean, the larger the variance in the numerator between group variances. So further away, let's say we had a 15 and we had a 6, this numerator would become larger. The group means are different when they are further apart. So mean squared error for between groups was about 15.54. And the meaning of this number is not intuitive because it is the sum of squared distances from the global mean divided by your degrees of freedom, which is number of groups minus 1. But it's important to note that if this number in the numerator will become larger if the averages of each group is more spread out. And that's what you need to understand. Now let's look at the denominator of within group variance. This variance measures the distance between each data point and its group mean. So we're looking at, for example, group 1, 11.203 is the group mean, and we can look at all the 10 pieces of data, and we are trying to figure out what the distance is. So it's sum of the squared distances divided by the degrees of freedom, which is sample size minus 1. This variance is small when the data points within each group are closer to the group mean, right? As data points within each group, within the group, spread out further, then the within group variance increases. Now this within group variance is your random error. Why are 2, 3, group 1 different from group 2, group 3, and group 4? That's what you can explain, because they are in group 1, group 2, and group 3. If there are 4 different drugs, you're saying, well, the difference is because of the different kinds of drugs you're going to use. But why is there a difference inside a group? You don't know. And that's your random error, and you want that to be small, right? So analysis of variance essentially looks at that ratio. So a large value of F makes things very significant. High numerator, low denominator. And if you look at common sense, you say, well, one group, the numerator talks about the difference between one group from the other, whereas the denominator talks about how they are different inside a group, and you want the ones inside the group, the denominator, to be low, and between groups to be high. And as error increases, which is within a group, then the differences essentially are because of this random error than because they are in different groups, right? So F statistics are the ratio of the two variants that are approximately, when they are approximately the same value, then null hypothesis is true, which means really there is no difference, which yields a F statistic near 1. So here is an example of low F value, right? You can see here. And here is an example of high F value where you look at these three groups, 9, 10, and 11. They're very close to each other. And so you will find that your numerator is small and then your denominator was whatever it is. But however, here, because these groups are widely separated, your numerator is going to be a lot larger than the other value, right? So low F value graph is this. Group means cluster tightly together, and the distance between the means is small relative to the random error within each group. And so you can't really say that one group is different from the other. Whereas in high F value graph, they are more spread out, and so you can actually start differentiating between the groups. All right, so F test in one-way ANOVA. Here, and we talked about it, the F value is 3.3, indicates that the between group variance is 3.3 times the size of within group variance. And null hypothesis is that the variances are equal, and therefore is 3.3 large enough to reject the null hypothesis? Well, we can compare this 3.3 to the F critical, which was 2.866. Yep, it is large enough. Or use the p-value, which is 3.11%, which is less than alpha, and say, yes, it's different, right? So now let's take an example and see how we're going to do this in Excel. So here is an example. We have Sunnydale Bank has 4 branches, and they're evaluating the performance across different branches. Now, the speed at which they complete a transaction is being measured, and that's what's in your Excel file. They randomly select a sample of 30 customer transaction recordings from each of the branch and focus on how fast the transactions are resolved. And they assume type 1 error is 5%. So we'll go very quickly to the Excel file to take a look at the data, but let's start looking at 4 branches is 4 groups. So this is a single factor ANOVA because we're looking at whether there's a difference in performance across different branches and how fast they are doing customer transactions is what we are looking at. So hypothesis is performance across all 4 branches are different. Null hypothesis is they are not different. Type 1 error is you conclude that they are different when they're not. Type 2 error is you conclude they are not different when they are. And alpha we are looking at is 5%. Now before we get into Excel, and I'm going to do that right now before we look at this again. So let's stop here and go into Excel. So here we have the Excel data set, groups 1, 2, 3, 4. We go into data analysis. We are going to look at ANOVA single factor and your input range, and focus very carefully here. Remember, I'm not selecting this number here. I'm just selecting this part, and this is going to be important. What you're selecting is going to be very important when you do the other 2 ANOVAs. So labels in the first row, which is there, you're going to click. I normally like to click it in the same, and that's what I've done here. But let's just go to create a new worksheet right now because I want to talk to you a little bit about formatting. So when you get something, a report like this, you'll notice that a lot of it has, what you want to do is kind of format it so it looks kind of a little clean. Maybe 4 decimal places. Sum of squares can also go as numbers with 4 decimal places. Here we go. F critical again. Go ahead and put 4 decimal places. And here's the p-value. Notice this E minus 0.7. A lot of you get into trouble when you see this. Make sure this is a percentage value, and that way you know what the value is. Okay, so make sure you have this, and this is how you create your report. And I'll talk about how we're going to read this report when we switch back to PowerPoint. So you saw that in Excel, how we did ANOVA, select all data, not select the column which has just the serial number. Make sure if you selected the headings, you put labels in first row, enter the alpha value, and either put it in an output range or in a new sheet. Then when you look at the results, you can do some comparisons here. So we have 30 in each group, and Excel kind of requires ANOVA to have equal values. If there are unequal values, Excel cannot handle it. The average is given to you: 5, 4.8, 4.25, and 4.96 minutes. And then the variance is given to you. You can use this variance to calculate standard deviation, which is the square root of the variance. And standard deviation makes more intuitive sense. So if you look at it, groups 1, 2, and 4 are very closely clustered together, the averages, whereas group 3 is very far away. And it's probably because of group 3 that we are getting a significant value. I think if we removed group 3 and tried 1, 2, and 4, this p-value may not be significant, but I'm just guessing here. But that's because this is 4.25. The standard deviations are somewhere between 0.2 and 0.27, right? And so this is all pretty close, clustered pretty close together, except for this. So here are between group sum of squared, within group sum of squares, the degrees of freedom. So when we divide this value by this, we get the mean squared, and that gives us the F value. So obviously there's very little fluctuations compared to the between groups within the group, and that gives us a large F value, and F critical for 5% is 2.68. P value is 0, reject null hypothesis, and we can move forward. So we know that there's a difference here, but we don't know which one is different. Are all 4 different from each other? Just one? We can look at the data and suspect that 3 is the one which is different, but really we don't know. And there's something called Posthoc Tests, which is there in more sophisticated software, which is not available in Excel right now. So let's talk about what these Posthoc Tests are. So what we did was called the omnibus test. It's broad overall, p-value less than alpha, reject null hypothesis, statistically significant. So then we have 4 groups, right? And 4 groups have 6 comparisons. You can compare 1 and 2, that's a t-test. 1 and 3, another t-test. 1 and 4, another t-test. 2 and 3, another t-test. 2 and 4, and 3 and 4. So 6 comparisons. So if you had n groups, in this case n is 4, you see you have 6 comparisons. So let's say we have 5 groups. This would be 5 times 5 minus 1, which is 4. 20 divided by 2, that would be 10 comparisons. So when you have these number of comparisons, the error rate, essentially, given alpha is 5%, the error rate increases. This is the formula. And so error rate goes up to 26.49% if we allow alpha of 5%, right? So if we wanted error rate of 5% with 6 comparisons, then alpha, if we do the mathematical equation, we need to set alpha to 0.85%. Let's look at how big the comparisons grow. You have 2 groups, you have 1 comparison, error rate is 5%. 3 groups at alpha, 5%, goes to 14. 4 groups we already did, and you notice 6 groups, 53%. So you notice that the error rate increases quite dramatically. And if the error rate increases, we're just going to say there's significance even when there is no significance, just by random chance, right? So this is a problem. So there are multiple post-hoc tests. There's 2 keys method, Games, Howell, Dunnett, Schiff's, pairwise t-test, Bonferroni's method. And what these do is they essentially control the alpha and make sure alpha stays at 5% by doing the comparisons at a p-value at a much smaller rate, like we talked about, at 0.85%. So only when we do pairwise comparisons and we keep p-value at 0.85%, and if they are different, less than 0.85, it's significant. Otherwise, it's not significant. Unfortunately, these are not found in Excel. Now, you can use other plugins or you can manually do it. Here are some of the plugins in Excel. Realstatistics.com is a free plugin. Excel Stat is quite expensive. There's Minitab. There's other powerful analytics software, SPSS, SAS, R, which all can do that. But it's not here. So for this particular setup, we can essentially do multiple t-tests, 6 t-tests with the alpha of 0.85%. And if your p-value is less than 0.85, we can say those two groups are different from each other, right? So we will stop one single factor ANOVA. Remember, when you have, it's only one variable, but when you have more than 2 categories in that variable, you are going to use ANOVA instead of your t-test.